Homework 3.4, the rational zero theorem, zeros of polynomial functions, video 5. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. The following video associates directly with questions 8, 9, and 10, meaning that they ask you exactly what this one does, but is also parts of 11 through 14. In the previous video, I mentioned that this function would not have any positive zeros because all the values were positive, and so putting in a positive number would keep everything positive, no chance of equaling 0. But there's a broader statement you can make about the number of positive zeros or the number of negative zeros that a polynomial function can have. And that broader statement is called Descartes' rule of signs, named after French mathematician and philosopher René Descartes, who's responsible for things like graphing and also for saying things like, I think, therefore I am, which reminds me of a nerdy joke. René Descartes walks into a bar. The bartender asks, would you like something to drink? He says, I think not, and then he disappears. Think about it. All right. So what is Descartes' rule of signs? Well, it's easier to do than it is to explain, so don't panic when I read all this to you. Suppose f of x is a polynomial function written from highest to lowest power. So no trickery, highest power, next highest power, all the way down to the end. Don't mix up the terms because keeping them in order matters here. Descartes' rule of signs says two things. The number of sign changes in the function, meaning as you go from term to term, the number of times the signs change between positive and negative. I think they're mowing out there. I hope that doesn't make this hard to listen to. 1 second. They are. I'll speak up. So, the first part of Descartes' rule of signs says the number of sign changes in this function as you travel from term to term, or that minus an even number, is the number of positive real zeros of the function. So for example, let's count the number of times the sign changes as we go from term to term. Positive, positive, did not change, positive, did not change, positive, did not change. So there are 0 sign changes. And that implies that there are 0 positive real zeros. Now, I can't do the minus and even number part of this because this would 0 minus an even number will make it negative. You can't have a negative number of zeros. And the second part of Descartes' rule of signs almost says the exact same thing with 2 subtle changes. The number of sign changes in f of negative x, in other words, if I change all the x's to negative, or that number minus an even number, is the number of negative real zeros of f of x. So in order to count the number of negative real zeros, you have to first evaluate what is f of negative x. But that's easy to do, because putting a negative on an odd power will keep the negative and therefore change this number's sign. And putting a negative on an even power, the negative gets squared and disappears. So in other words, when you put in a negative x, only the odd power's coefficients change signs. So the 2x cubed would become negative 2x cubed, its power was odd, but the positive 5x squared will stay positive 5x squared because its power was even. The positive 6x becomes negative 6x because its power is odd. And this doesn't even have an x, so it's not going to change. So once you evaluate f of negative x, which is equivalent to changing the signs of all the odd-powered terms' coefficients, then count the sign changes. This time I'll draw some arrows. From the first term to the second term, the sign changes. That's 1. From the second term to the third term, the sign changes. That's 2. from the third term to the fourth term, the sign changes. There are 3 sign changes. And what does that mean? That means that there are 3 negative real zeros, but that number is large enough that we can subtract an even number from it, or the only even number we can subtract from this and keep it positive is 2. 3 minus 2 is 1. Negative real 0. And if you recall from the previous video, there was one negative real 0. In fact, it was rational, it was negative 1/2. But Descartes' rule of signs can give you the ability to know what to look for or what to not look for. The fact that there were 0 sign changes here means that there were no positive real zeros. The fact there were 3 sign changes means either there's 3 negative real zeros or 1 negative real 0. And by the way, the reason you subtract an even number is because we're counting real zeros, but some of them may be complex. Complex numbers always occur in pairs. Why? Because they come from the quadratic formula. And when you do the quadratic formula, if the discriminant is negative, then you will get not 1 but 2 imaginary numbers. So when you lose a real 0 in place of a complex 0, you lose 2 of them at a time, which is why you always subtract an even number. Let's take another look at a quick example of Descartes' rule of signs. Again, it's really much easier to do than it is to put into words. But let's take one, and I'll grab one off the homework. How about let me look at it and see which ones that you see. Let's take a look at number 10. Well, your number 10 won't be exactly like mine, but it'll be similar. F of x equals 7x to the 4th minus 6x to the 3rd minus x to the 2nd minus 7x plus 3. Now, let's go ahead and calculate f of negative x. And remember, all that does is change the sign on the odd-powered terms. So the 7x to the 4th stays the same. The negative 6x to the 3rd changes to positive 6x to the 3rd. The negative x squared stays the same. The negative 7x becomes positive 7x. And the positive 3 stays the same. So let's count sign changes, starting with f of x. From the first term to the second term, there is a sign change. It goes from positive to negative, but not from the second to the third, nor the third to the fourth. However, from the 4th to the 5th, there is a sign change. So 2 sign changes means there is 2 or this minus an even number. 2 minus 2 is 0. 2 or 0 positive real zeros. So there may be some or there may not be. Let's count the sign changes here. From the 1st to the 2nd, it doesn't change, but from the 2nd to the 3rd, it does. And from the 3rd to the 4th, and that's it. So same thing here. 2 sign changes, or this minus an even number, 2 minus 2 is 0, negative real zeros. So how can this help you? Well, let's say you're doing synthetic division and 5 works. 5 is a positive real 0. There must be another real 0, positive real 0, because there had to be 2 or 0 of them. And if you found 1, then it can't be this, so it must be that. It's possible this could have no real zeros at all, and they could all be imaginary. That's a much tougher nut to crack when a function has all complex zeros that aren't real, and it's beyond the scope of this course. So you can rest assured that in any problem where you're asked to find the zeros, there will not only be a real one, but a rational one that allows us to use the rational zero theorem.